Welcome back to the deep dive. So we've spent, a lot of time on classification,
Hmm.
predicting whether something belongs to group A or group B, the classic cat or dog, or is this email spam or not spam?
Right, predicting which group something falls into.
Yeah.
But the stack of sources our listeners shared this week, they force us to switch gears completely.
A whole different mindset. We're moving from predicting a group to predicting a specific continuous number.
Exactly.
This is the world of regression analysis. And our mission today is really to unpack the models, the tools you need to accurately predict a numeric outcome, which, let's be honest, is often where the real business value is.
Absolutely. The applications in the source material are, well, they're massive. You're talking about predicting insurance premiums, making weather forecasts,
Forecasting sales for the next quarter.
or the classic high-stakes challenge,
Yeah.
right? Predicting housing prices or what the stock market is going to do.
To keep this all grounded, we're going to be exploring everything through a really great data set, the Ames housing data set.
Yeah, it's residential property data from Ames, Iowa, over a few years. It gives us a ton of features to work with to try and nail that final sale price.
Okay, so let's start with the basics, the linear foundation. When we talk about regression, the big idea is just drawing the best possible line through the data, right?
Precisely. The goal is to model the relationship between your features, one or many, and that continuous target variable. And the absolute foundation is simple linear regression.
Simple meaning just one feature.
It's just one feature, we'll call it $6, predict your target.
And that's the classic equation we all remember from high school math, right? The y equals mx plus b, but now we're calling them weights.
We do, yeah. It's 180A W dollars plus W1x3. That $2 is your baseline, your y-axis intercept. It's the value of yay if $6 were zero.
And w dollar.
That's the weight coefficient for your feature. It's the important one. It tells you how much E changes for every single unit change in $6.
So if that weight, w dollar, is huge, it means that one feature has a massive impact on the price.
It could, yeah. And the whole point of the analysis is to learn the best possible values for those weights. If we do that, we've found the best fitting straight line. We call that the regression line.
But the line is never going to be perfect. There's always going to be some error. You've got the real data points, the dots, and then you've got the line, your prediction. What do we call those little vertical gaps between them?
We call those the residuals,
Yeah.
or sometimes offsets. They literally are the prediction error.
So a great model has tiny residuals.
And a perfect model has zero residuals,
Huh.
which, never happens.
Of course not. And in the real world, a house price isn't just based on one thing. So you immediately have to scale up to multiple linear regression.
Right. You move from one weight to a whole collection of them, one for each feature. The math generalizes pretty cleanly, but the big problem is visualization. It just breaks down.
You can't draw a line anymore.
Nope. You're trying to picture a fitted hyperplane in a high-dimensional space. So you stop trying to see it, and you just focus on the math of finding the best set of weights. Thaller's dollar.
Okay, so let's dig into the Ames data. We need to find the features that are going to give us the best rates. It's a rich data set, right? Almost 3,000 examples, 80 features.
It is. But for this deep dive, we're focusing on the heavy hitters for predicting sale price. So think things like overall quala.
That's the 1 to 10 rating for materials and finish.
Exactly. Then there's overall quantas, the condition rating, GR live area, that's your square footage, and total BMTSF, so total basement area.
So we have the features, we have the target sale price, and we have the model structure. The huge question is, how do we find the best weights? How do we make those little error lines, the residuals, as small as possible?
We use a method called ordinary least squares, or OLS. It's simple, it's powerful, and it tells us exactly how to measure best fit. OLS works by minimizing the sum of the squared vertical distances.
Okay, wait, why squared? Why not just minimize the distance itself? Why that extra step?
That is the core insight, and it's so important to get. OLS is designed to minimize the mean squared error, or MSE. We square the error for two reasons. First, it gets rid of negative values, so an error above the line and an error below don't just cancel each other out. But the main reason, and this is critical, is that it acts as a punishment function.
A punishment. Okay, so it punishes large mistakes.
Exactly. A prediction that's off by, say, $10,000. Once you square that, the error becomes mathematically way, way bigger than two separate misses of 5,000 each. MSE forces the model to obsess over not making those huge, embarrassing mistakes.
So OLS tells us what the best line looks like, but we still need an algorithm to actually go find it. And that's where things like gradient descent come in.
Right. Gradient descent, or GD, is the classic. It just iteratively tweaks the weights, taking these tiny steps down the error curve until it finds the absolute bottom, the minimum MSE.
But it's slow.
It can be very slow.
Yeah.
Because it has to look at the entire data set to calculate the error for every single tiny step it takes.
And that's why people use stochastic gradient descent, SGD.
For big data sets, yes, absolutely.
Yeah.
Instead of the whole data set, SGD grabs a random little batch of data to calculate the error and update the weights.
So it's an approximation.
It is, and that makes it a lot faster. You sacrifice a little bit of precision on each step for this huge gain in speed. It's the practical choice for most big data problems.
Okay, so before we jump into actually running the model, the source notes really stress something. You have to look at your data first. Exploratory data analysis, or ED.
It's non-negotiable. It's how you spot outliers, understand how your data is distributed, and see relationships between the features.
And a great tool for this is the scatter plot matrix.
Oh, it's brilliant. It lets you see all the pairwise correlations between your features in one go.
Yeah.
And then down the diagonal, you get a little histogram for each feature so you can see its shape.
And looking at the Ames data in that matrix, one relationship just jumps out at you. There is a clear, strong, upward-sloping line between GR live area
The living space.
and the sale price.
And to put a number on that visual hunch, we use the correlation matrix, specifically the Pearson correlation coefficient.
And that's the number that goes from -1 to +1.
Right. -1 is a perfect negative correlation, 0 is no correlation at all, and 1 is a perfect positive correlation.
For the Ames data, the GR live area has a correlation of 0.71 with sale price. That's a really strong signal.
It is.
Yeah.
But this brings us back to the problem we just talked about. Because OLS squares the errors, it's super sensitive to outliers.
Right.
One single weird house, maybe it's huge but priced super low, can literally pull your entire regression line off course. And while you could remove those outliers by hand, that takes a lot of time and domain expertise.
Okay, so what do? We need something tougher. The notes point to a really clever alternative for messy data, random
sample consensus, yes.
Yeah.
It's almost like, think of it like a jury trial for your data points.
Okay, I like that. So it's trying to find the reliable witnesses.
Precisely. It's designed to fit a model by focusing only on a reliable subset of the data, which it calls inliers. It actively tries to ignore the outliers, the bad actors.
So how does this ransack jury process actually work?
It's an iterative loop. It starts by grabbing a few random data points and says, okay, you guys are my initial inliers. It fits a temporary line just to them. Then it tests all the other data points against that temporary line. Any other point that's close enough within some tolerance you set gets added to the inlier group.
So it's constantly growing its group of trusted points.
Exactly. Then it refits the model using all the current inliers, and it checks the error. If the error is low enough, it stops. If not, it throws that group away, starts with a brand new random sample, and does the whole process again.
Until it finds a consensus.
Until it finds a consensus fit that a majority of the data agrees on. It's a really robust self-cleansing approach.
So once we've built a model, we have to evaluate it. And we have to do it on data it's never seen before to avoid
Fitting.
overfitting.
And since we can't just look at a hyperplane, we need other tools. The most important one is the residual plot.
Okay, so what is a residual plot showing us?
It's a chart of the errors, the residuals plotted against the predicted values from the model.
And what do we want to see? What does a good plot look like?
You want to see complete random chaos, just a random scatter of points around the zero line. If you see any kind of pattern like a cone shape or a curve, that's a huge red flag. It means your model is making systematic mistakes.
Interesting. Now, we talked about MSE, but the sources also mention another metric, mean absolute error, or MAE. Why would we use that instead?
Well, MAE is...
Yeah.
It's just more straightforward. It's the average of the absolute differences. If your prediction is off by $10,000, the error is $10,000. Full stop. It doesn't have that punishing square term.
So it's easier to interpret.
Much easier.
Yeah.
In finance, for example, they often prefer MAE because you can report the error in dollars, which is something a client can immediately understand.
And if we're looking at these error metrics, what does it mean if our training MSE is super low, but our test MSE is huge?
That's the textbook definition of overfitting. Your model basically memorized the training data, noise and all, and it completely failed to generalize to new data. You need to simplify your model.
And because the number for MSE depends on the scale, like using thousands of dollars gives you a smaller number than using dollars, we need a standardized measure.
Right.
Which brings us to the coefficient of determination, or TER dollars.
22 is the universal interpreter. It basically tells you how much of the story your model is explaining. It's the fraction of the variance in your target variable that your model actually captured.
Can you break down the formula for us just conceptually?
Conceptually, $20 is just 1 minus a ratio. On top, you have your model's total error, its mistakes. We call that the sum of squared errors.
Okay.
And on the bottom, you have the error you get from the dumbest possible model.
Which is just guessing the average every time.
Exactly. So $20 is basically a score of how much better your model is than just guessing the average price for every house.
So a higher 22 is always better.
Always. And $20 means your model is perfect. And $20 means your model is completely useless, no better than that dumb average. It's a really clean way to communicate how good your model is.
Up to now, we've been assuming the relationship is a straight line. But what if it's not? What if the data really curves? That's where polynomial regression comes in.
Right. This is how we can model nonlinear relationships. We basically turn that straight line into a curve by adding new terms to the equation, like in 6.2 term or in 6.3's term.
Now, the sources pointed out a really crucial detail here. Even though the line on the chart is curved, it's still technically considered a linear regression model. How does that work?
Because it's still linear in the coefficients and the weights. You're just creating a transformed version of your feature before you apply the linear model to it.
I see.
We actually tested this on the Ames data, comparing a quadratic and a cubic fit for sale price versus GR live area.
And for that specific relationship, it didn't really help much, did it? The line was pretty straight to begin with.
It was, yeah. But that doesn't mean the technique isn't useful. If you were modeling price against, say, the age of the house, you might see a real curve there. Maybe depreciation accelerates after a certain point. A polynomial term could capture that perfectly.
So if that's not complex enough, we can look beyond linear methods entirely and move to tree-based models, like the decision tree regressor, or DTR.
The DTR is a totally different beast. It has some advantages, sure. You don't need to do as much data transformation. But the predictions it makes are, visually, they're a little jarring.
Jarring how?
Because it makes predictions in these discrete steps. It doesn't create a smooth line.
Yeah.
It might say any house between 2,000 and 2,500 square feet costs exactly $350,000.
So the prediction line is all jagged steps.
Exactly. It's a series of flat, horizontal lines. It doesn't capture the continuous nature of the housing market at all.
And I've heard DTRs they're really sensitive to how deep you let them grow, right? They overfit like crazy.
Oh, absolutely. If you let that tree get too deep, say 10 levels deep, you could end up with leaf nodes that are making a prediction based on maybe 2 or 3 houses.
Yeah.
That's not going to generalize at all. We have to control the complexity with things like max leaf nodes.
So that's the whole idea behind moving from one fragile tree to an army of them, leveraging random forest regression.
RFR is probably the dominant ensemble method here. You're combining the predictions from hundreds of different decision trees, and each one is trained on a slightly different slice of the data.
And all that averaging smooths things out.
It does. It gives you much better generalization performance because the model variance drops. They're also less sensitive to outliers, and frankly, they require a lot less careful tuning than one single deep decision tree.
And beyond just raw performance, random forests give you something that linear models struggle with, a clear ranking of which features are most important.
The feature importance attribute, yeah, this is huge. The model literally gives you a score for each feature, ranking it by how much it helped reduce the error across all the trees in the forest.
So you get an actual numerical ranking.
You do. For a real estate developer, knowing that overall qual is, say, twice as important as total BMT-SF, that's incredibly actionable information.
And you could use that ranking for feature selection to build a simpler model later.
Absolutely. It's a fantastic starting point. You can take your top 5 or 10 features from the random forest and then build a leaner, faster model for deployment that still captures most of the predictive power.
Wow. We have covered a huge amount of ground today. From the simple elegance of a straight line all the way to a whole forest of decision trees.
We really have. We started with that core idea of minimization, how OLS aggressively punishes big errors. And then we looked at how to make our models tough, how to handle dirty data using Ransac's consensus approach.
And we gave ourselves some powerful tools to diagnose our models, like residual plots, and a really clean way to interpret their performance with $2 too.
And in the end, I think we saw that for complex problems, sometimes the best answer isn't a single, perfectly tuned model, but an ensemble. A method like random forest that gives you better performance and this incredible interpretability.
Right. It was so interesting that for the Ames data, adding polynomial complexity didn't help much, but the random forest approach was a clear winner. And that leaves me with a final thought for you to take away. We saw the power of collaboration here, of combining many imperfect models into one robust solution. So in your own field, where might collaboration and ensemble beat individual genius? A single complex equation. Something to think about until our next deep dive.